Thank you. I want to thank the steering committee for the opportunity to speak here. And here I'm going to discuss some of our recent studies of gravity waves using a mesoscale-resolving WACA model. So I would argue that study of gravity waves is one of the central themes for CEDAR research, and for good reason. We know that atmospheric gravity waves, they can drive the circulation from the middle to upper atmosphere, and also they can interact with large-scale waves, tides and planetary waves, change their phase and also amplitude. And when they get to the thermosphere and ionosphere, they can cause very large disturbances and even produce irregularities, some subject under very active research. And on the small scale, they can produce instabilities and lead to turbulence, and therefore change the mixing, as the previous talk kind of alluded to at the end. And the challenge or difficulty is that it is not an easy task to kind of try to capture the waves from its source all the way to the impact region in a global context. And I just try to illustrate this point by showing some previous results. Stephen Smith, they have their OH imager, all-sky imager in the Andes, and they capture this very nice wave, supposedly orographic wave above the Andes. And this is a more recent study also from the OH emission, but from satellite view, from the SUMI MPP observation. And Yu et al., they analyzed the gravity wave there, a small scale to very large scale gravity waves, kind of likely related to a deep convection. And if we put them in the context, kind of the global context, and especially compare them with the tidal features, here maybe the DE3, famous DE3 tides, we can kind of appreciate the very large span of the scales from the gravity waves to very large scale waves. And this is how to fill the gaps. I mean, here is a mesoscale and even microscale. You can barely see them in the global context, but they exist globally, everywhere. And so they can have a large impact for the global dynamics, as we mentioned earlier. And the other thing is that their source can go down in the troposphere. And kind of this, if we look at the different scales, reminds us of the Russian dolls. One similarity is that the small pieces are also the center pieces. And so to kind of try to capture all this, you really need a global model that can resolve down to mesoscales and also down to the troposphere where the source is, the upward coupling like Mike Mandillo mentioned earlier. So this is why we try to kind of look at this problem using some new model setups, model technology. And so the WACA model is the NCAR whole atmosphere community climate model. And in this study, we're using their new dye core, the spectral element core, solved the Earth atmosphere on a cube sphere, so there's no polar singularity. And we set up a model so that the horizontal resolution is a quarter degree, about roughly 25 kilometers globally. And vertically, we have 1/10 of the scale height, which is roughly half a kilometer vertical resolution. And the model scaled pretty well, thanks to the modern technology of the computers and also the software. It can scale pretty well above 10,000 cores. And I want to mention that in all this, most of the simulations, we have turned off the gravity wave parameterization so that we can evaluate the resolved waves. And we have, so far we have completed a 1.5 year model year run, so that we can start to look at the seasonal variations. So the first thing we looked at is the vertical winds, which is a good proxy to gravity waves from the tropopause all the way to the lower thermosphere. So here you can see a lot of hot spots, likely due to the deep convection in the tropical region. And here, for example, there's one very large one with a very large vertical motion due to the development of the tropical cyclone east of Australia. And then in the stratosphere, we began to see the rain or partial rain structures associated with this different convective sources. And as altitude grows, we can see that both the amplitude and the spatial extent of the waves start to grow. And by the time it reaches the lower thermosphere, it can cover almost the whole Pacific region. And at high latitude, we can also see a very large, strong, more complex wave structures are kind of corresponding very well with the polar winter jet. And here you don't see a lot of wave activity in the tropopause. So this is likely generated from the adjustment of the jets. And just some more detailed look at the different scales and different wave processes. So this is at the later stage of that development of the tropical cyclone wave. And at the leading edge, or the far reach of the wave, the scale is near 1,000 kilometers. But also there are smaller scale waves related to different convections, for example, in North Atlantic, over Brazil. And at high latitude, I just mentioned this, the stratosphere jet. I should emphasize this is again in the lower thermosphere, about 100 kilometers. But the signal of the jet generated wave is still pretty strong. And also orography, or maybe the secondary wave from the breaking of the primary orographic waves over the Himalayas and the Rockies. And also very small scale structures, probably from the breaking of the gravity waves. And this is an animation, 3-day animation of the meridional wind at about 95 kilometers. And you can see the whole kind of life cycle of the development of the tropical cyclone gravity wave, and also their breaking at the end. And on large scale, you can almost see this sweeping, or large scale feature sweeping from west to east, which is tides. And at high latitude, you can see this very strong, robust generation of gravity waves. And this is just a different perspective from the North Pole, and again in the lower thermosphere, very strong generation of waves, and interacting with the waves propagating from low latitude. This one is from the tropical cyclone, but apart from that, also other convective systems with the smaller scale waves. And just for comparison, this is also meridional wind from the same simulation, 3 days near the surface. And just want to point out that this has a very typical 2D turbulence kind of feature. And also the temporal feature is much slower compared with the upper atmosphere. So the dynamics and the feature of the dynamics are quite different between the lower and upper atmosphere. And this is a simulation for July. And first in the stratosphere, this is a 10 hectopascal. And you can see this development of a typhoon at that time and how it was producing waves higher up. And also along the continents, you see a popping up of concentric gravity waves here and there, probably due to the deep convections here. But at this time, the largest wave feature is in the southern hemisphere. Here is a very strong wave generation, likely again related to the jets. And sometimes the jets interact strongly with the orography, either Andes or here is the Antarctic Peninsula, and generate very strong gravity waves, orographic waves. And I remember maybe in 2009 or 2008, Professor Mike Mandillo visited NCAR and asked us if we could model this over the Andes. So it took a few years for us to answer his challenge. And this is again in July, but in the mesosphere, lower thermosphere. And what's different from the previous, the January-February case is that we do not see a very large response of the tropical cyclone system, or the typhoon, response to the typhoon here, probably because of the different wind systems. So sometimes the waves can make it to the mesosphere, but maybe sometimes it got filtered out or only have a weak signal. And but here in the southern hemisphere, still very strong wave activity related to the probably the jets, and also the orographic wave can propagate quite high into the mesosphere. Probably that's what Stephen Smith they see from their imager measurement. And this is to look at 4 levels from the South Pole. Again, tropopause, stratosphere, mesosphere, and lower thermosphere. And what's interesting is that here you can see this very clear wave number 5 or 6 baroclinic eddy kind of going along the jets. And whenever the system, the jets related to the eddy interact with the orography, you start to see generation of waves. And just to highlight a few, let's see, oh here. Yeah, one of them is that when the eddy was interacting with the Andes, you see response of the wave higher up in the stratosphere and mesosphere. And this is when it's over the Kerguelen Islands. You see this wave fronts here, and also penetrating all the way to the mesosphere. This is a case kind of studied by John Alexander a few years ago using airs. They saw the very strong wave propagation from this island to middle and upper atmosphere. And this is over New Zealand. Don't see a lot of signature here in the mesosphere, but definitely some signature in the stratosphere. And this is for when the eddies was interacting with the Antarctic Peninsula. So also we looked at the spectral structure and its dependence with altitude. So we look at the zonal wind spectral density from stratosphere all the way to the lower thermosphere. And lower down you can clearly see this very steep slope, -3, typical of vortical mode or 2D turbulence. And when you go to higher altitude, the spectrum becomes flatter. So this is more of a divergence mode, or the gravity waves. And also it tells us that the relative importance or power at smaller scales, mesoscales, becomes increasingly important with altitude. And also we note that beyond about 10 delta, about 200 kilometer, you start to see a much sharper drop of the power, which indicates that for this model, the effective kind of range we can resolve for the mesoscale is about 10 delta, about 200 kilometers. And then we compare this with the regular or 2-degree resolution WACOM. And so this black line is the high res, and the gray line is the lower resolution or 2-degree resolution. And if we look at them, we see that the relative powers of the two are in pretty good agreement up to about 14 delta. At the mid-latitude, it's about a couple of thousand kilometers. And above that, the 2-degree model was giving power it drops very fast compared with the high res. So that tells us that if we look at the different wave regimes, the low res model or the 2-degree model can resolve the tides and planetary waves and probably also the synoptical waves pretty well, but they will miss a lot of or most of the inertial gravity waves. Of course, they will miss the mesoscale waves too. And this is a possible reason for a lot of the chemistry climate models were missing QBOs and also were producing bias in the southern polar stratosphere, the cold pole bias, because there's a large missing force from the missing of the inertial gravity waves. And also in this physical space, we can look at what's the implication for a low-res model. This is a high-res model. We're looking at the PDF, the probability distribution function. And this is for total horizontal wind. And this is for the vertical shear of the horizontal wind. And this is a high-res model. And you can see the dynamical range from the high-res model cutting this off, is at 100 kilometer at equator. So there, in the lower thermosphere in the equator, the dynamical range is between 0 and 200 meters per second. While if we look at the regular res, we'll get at most about 100 or 120 meters per second. And the difference is even larger for the vertical shear. And the dynamical range for the vertical shear is more than, for the high res, is more than 80 meters per second per kilometer, while for the regular res, it's about 20 meters per second per kilometer. On the other hand, at lower altitude, at 30 kilometers, the difference is not so large because of the dominant mode there is large scale still. And this has important implications because the lower thermosphere is obviously a very important region for both dynamical reasons and also for electrodynamical reasons. It's the E region, dynamo was occurring there. So this is a very famous graph plot from many years of rocket measurement, and from there, Miguel Larsen was able to deduce the wind shear, and he found that there's a wind shear peak at about 100 and 110 kilometers. And theoretically, we can kind of explain that in terms of the static stability, because that static stability also has a peak exactly at that place. But in the models we have run in either time GCM or Wacom, we can never reach that theoretical peak value. So from here, we can say probably this is because of the missing of the mesoscale wave, which is a main driver for those large shears. And then we want to know that how well the model is really doing in terms of comparing to observations. So here we compare the energy density, potential energy density from the model in January and April with that deduced from a SABRE measurement. So in general, actually, the two agrees quite well. They're on the same or very similar color scale. And in both cases, you see these two branches in the summer and winter peak in the energy density, gravity wave energy density, in good agreement with the observations. And both are consistent or they coincide with a large wind shear when the wind start to reverse, decrease or reverse. So in that sense, the two agree pretty well. And also in April, this large branch in the south agrees pretty well here. And also you see this peak at the equator kind of consistent with the SAO signal, the mesosphere semi-annual oscillation. And it showed up both in model and also in the observations. And on the other hand, if we try to evaluate the wave forcing, impact on the mean zonal wind, we see there's still some problems or deficiency. And on this side here, the solid line is the zonal mean zonal wind from the high-res model. And the color contour here is the forcing in terms of meter per second per day. And this one is more like a climatology. This is from a data simulation Wacom with a regular resolution, but incorporating or simulating both lower atmosphere and upper atmosphere, SABRE and MLS data. And so it's very close to our understanding of climatology. And we can see that the jet is not closing at the right altitude. So in other words, at the same altitude, we're not producing the sufficient forcing to reverse the jet in the summer hemisphere or in the winter hemisphere. The winter hemisphere, the jet slows down but never reverses. So the quick summary of the things I've just said, the mesoscale-resolving Wacom could be a very useful tool for getting insight of the gravity wave dynamics in the middle and upper atmosphere. And obviously from the simulation, both the spectral structure and just the physical space, we can see that it plays a very increasingly important role in the upper atmosphere. And some of the impact are not accounted for in regular res models. And we start to evaluate the model from the waves from the model, and energy-wise, it seems that it's doing a reasonable job, but the momentum budget, it's still missing some important waves, maybe deep in the mesoscale. And of course, it will be an interesting question to ask, as we asked at the beginning, what's the impact of this mesoscale waves on the ionosphere and thermosphere system? We're not there yet, but we're making some good progress. Recently, we have put in an important piece in Wacom, which is the interactive electrodynamics and plasma transport. So for example, here we're getting, this is a vertical drift as a function of local time and latitude, getting upward in the daytime, downward at nighttime, a pretty reversal enhancement, and a pretty well-defined EIA, the equatorial ionosphere anomaly from the model. So we can check the poster Tuesday, tomorrow, by McNerney et al. So of course, this is still regular res, and we hope that a few years, hopefully not too long, we'll combine the two development and try to answer the question we're asking. And I want to acknowledge the CESM and the WACON team, my colleagues at HAO, ACOM, and CGD at NCAR. For the high-res work, these are my co-authors, Joe McNerney, Sean Santos, Peter Lorenzen, Mark Taylor, and Nick Patatella. And this work is obviously supported by CEDAR, very important support, and also the NASA LWS Strategic Capability Fund. And the simulation time is provided by the NCAR Strategic Capability Award. Thank you.